All right, everyone. Welcome back to Bio 1120. I'm surprised to see so many of you here. Did you not understand on Tuesday when I said all these are recorded and you can watch them from the comfort of your own bed wearing pajamas pretty much whenever you like? But nonetheless, it's good to see so many of you here. Again, welcome back. What did you think about our sound test this morning? Is that, for those of you who got here a few minutes early, is that a good way to start the morning? I was saying to a few people in the back, boy, I wish I had a sound system like this at home. I mean, this is pretty cool. You can have some nice parties in this room if you got the keys, and I can help you out on weekends if you need to get in here. All right, well, so it occurs to me that there's something I should have told you on Tuesday that I forgot to do. It should have been high on my list, and I'm surprised nobody asked. It seems a very common question, is what's going to be on the tests, right? And so let me give you a very direct answer to what's going to be on the tests for this class, because I really do want you all to do very well on the tests, and I want to do everything I can to tell you exactly how to do well on the tests. So first, about how to do well on the test is, if I have not talked about it in a lecture, like the ones that are being recorded, like right now, if I haven't talked about it, I don't think it is fair for me to ask you about it on the test, right? And so that goes with some of the things that I was talking about on Tuesday. I'm not going to ask you what's on page 64 from the textbook, right? But you may have noticed in lecture on Tuesday, there were a couple paragraphs in the lecture notes about the scientific method, and I never even got to that. I didn't talk about it. I'll tell you right now, part of me wants to say something about the scientific method to fix that problem, but another part of me is saying, no, just keep moving and don't ask any questions about that particular content on the first exam that you see. And so I think that's what we'll do. Bottom line, if I don't say something about it during the course of the lecture, don't worry about it. That's not something that I'm going to be beating you up about with the tests. And then, while I'm talking about tests, I'm going to sound like a broken record to you pretty soon, but look at the old exams, right? If you want to do well in this class, and come on, who doesn't want to do well in a class? I cannot emphasize enough, look at those old tests that are available to you on Pilot. First off, you get 1 point of extra credit for even opening that folder. We'll know, we're watching, and looking at those old tests will be a huge help to you, and it's not too early to start, right? If you look at those old tests right now, you might say, gee, we haven't talked about this, I don't know what the right answers are. Don't worry about that. Just get a sense for the way the questions are phrased, the kind of choices that I give you, so that now when I'm talking about these things in the lectures, it might help you key in, oh, when he says he's focusing on concepts, maybe this is one of those concepts that he's talking about, and I should take a note about it or pay more attention to it, right? So if I don't talk about it, it's not going to be on a test, and the best way to prepare is to look at those old tests, and you can't start too soon looking at those old tests, okay? Now, speaking of tests, this is a happy, gentle kind of talk about tests. I asked you all to take a pre-quiz before we started this class. So the window to take the pre-quiz is closed, right? We're not going to be giving people 4 points anymore. If you haven't done it, sorry, you can still go look at the quiz, but your chance to get those 4 points is closed now. But we've gotten all the answers as of about half an hour ago, and I've got them in the first 12 slides here this morning. And what I'd like to do is, over the course of the semester, when we get to a lecture where I'm going to be focusing on one of the answers to those questions, I'll trot out the slide from the pre-quiz, and I'll say, hey, look, you guys don't need me. 85% of you already knew the right answer to what I think is one of the most important questions that I'll be addressing in the course of today's lecture. So again, why are you here? Go watch the recording, leave, go home. You don't need me, right? But we've already done one of these, and so I'm going to flash through all 12 right now, but there's two that I want to talk about. The first is the first question, and I was rooting for A to be the right answer. I'm asking what's the one thing that all living things on this planet have in common. That's a fairly conceptual question. Fairly. It's not one of my best. But I told you pretty directly and pretty plainly in lecture on Tuesday, what I'm looking for as an answer to that question is we all share a common ancestor. Not just you and me, and we do, right? Maybe 20, 30 generations ago for some of us, but we all share a common ancestor, maybe 100 generations for some of us. But even me and you and E. coli and my beagle share a common ancestor at some point in the distant past, billion or so years ago for the E. coli. But that's what I was looking for this particular question. The question that pertains to what I'll be talking with you about today is actually the second question in that pre-quiz. I asked you something about, what makes us tick? What kind of elements come together to make a human being? I say living things here. The numbers I'm going to be talking with you about today are fairly specific to humans. A couple people, see, this is the kind of answer I would have given if I got a pre-quiz where I was told that there were no wrong answers. A couple people went with earth, wind, and fire. I had to come up with a fourth one, air. I don't know, but a few of you, right? It's 0.5%. That's something like 5 people or so. Actually, 2 or 3 people bit on A. But here's a great example of why you guys don't need me. You're a whole lot better prepared for this class than I was giving you credit for, but I'm trying to gauge this. I'm trying to figure out how to pitch what I'm talking with you about. The right answer is, I think, unarguably B, and that's a big topic of what I'll be talking with you about during the course of today's lecture. So, you guys can sit back, relax. One of the main points that I'm going to be trying to convey to you during the course of today's lecture. I'm going to flip now through the next 10 questions. We don't have to worry about them today, but during the course of the semester, again, I'll start off some of the lectures by saying, hey, remember back before the class even started, this is what you guys thought was the answer to this question. Let's talk about it today. But today, the main topic at hand is I want to talk with you about this grand topic, the chemistry of life. Okay? You guys are going to learn so many disturbing things about me during the course of this class. You're going to go crazy with all the stuff you learn about me. Here's a confession I have for you. As an undergraduate myself, I was one of those poor, misled souls that got tricked, fairly literally. I'll tell you the story if you stop by and talk with me at some point. Got tricked into being, of all things, a chemistry major. Right? Luckily, I had some other people looking out for me, and I was able to plead my case, and I was able to salvage something that would help me for the rest of my life, and I pulled off being a double major. I had a major in biology and chemistry, but I suffered, fairly literally, for 4 years as a chemistry major, and the good that's going to come from that suffering, I hope, is that in the course of today's lecture, I'm going to be able to give to you what I think, and I'm feeling pretty confident about this. I'm going to give to you in the course of one lecture pretty much all of the stuff that's important that you would learn during the course of an entire year of freshman chemistry. And I'll throw in a couple things from sophomore, junior, and senior chemistry level classes as well, just for good measure. But between you and me, the chemistry department hates it when I say this. I don't think there's anything more you're going to need to get out of chemistry classes beyond what it is I'm going to tell you today. But that's the plan. I'm going to take you by the hand and give you the highlights and focus on the important things from biology's perspective about first-year chemistry. Not first semester chemistry, first-year chemistry. Okay? So I made a stink on Tuesday about biology being the study of life. Right? Fairly formal definition. Chemistry, in contrast, is the study of matter. stuff, but very formally, it's the study of matter. And when we're talking about matter, ultimately, we need to start at some pretty, fine level of detail. We should start by talking about elements. Okay, an element, well, got bad news for you. There are 92 different naturally occurring elements. It's bad news because as a chemistry major, at some point, you kind of have to spend some time studying and learning about each of those 92 elements. Okay? Takes a while. Some of them don't seem that important, right? They never show up. You never hear about them aside from the lecture in a chemistry class. But there are 92 elements. And what makes an element special is that they're comprised of atoms. And these atoms are the smallest pieces of matter that you can get. If you can't divide them any smaller and still have something that has the same chemical properties of that element. Right? So there are 92 different elements, 92 different atoms. They're the smallest units of matter that retain the characteristics of those bits of matter. Bad news, 92 elements. Good news, there are only 25 that we understand are essential for human life. Okay? So you can just set whatever, 67 of them on the trash heap. You guys as biology majors don't have to worry about the vast majority of the naturally occurring elements. 25 at most are going to be important for a biologist because that's all that our bodies use and need. And it gets better still because 25 are essential for life, but most of those 25 are needed in ridiculously tiny quantities. The reality is that 4 elements, and this was the question that you saw in the pre-quiz, there are just 4 elements that comprise 96% of the mass of your body and my body. All right, so let's take a look at those guys, because that's where we should be focusing our attention if we're talking about biology. Those 4 elements that comprise 96% of the mass of our bodies are oxygen, carbon, nitrogen, or hydrogen and nitrogen in rank order. You can see that oxygen actually is about 2/3 of the weight of our bodies. So an awful lot of the chemistry that goes on in our bodies is governed by things associated with oxygen. But if you guys get a good grip on the chemistry that's associated with those 4 elements, you will be able to fight your way through pretty much all the chemistry that's important for a biology course. And not just this biology course, pretty much any biology course. Right? These are the 4 most relevant chemicals in biology, atoms, elements in biology. And so a big part of today's lecture, I want to make sure you guys at a really fundamental level understand what makes each of those 4 atoms, those elements tick. What makes them special? How do they act? How do they act with each other? How do they act differently? That's the main focus of today's lecture, is what's going on with the chemistry of oxygen, carbon, nitrogen, and hydrogen. Okay? And if you guys want to get the A+ version of a biology education, don't stop with those 4. You don't want the 96%, right? Good news, if you want a 99%, you only got to go 4 more elements deep, right? Because calcium, phosphorus, potassium, and sulfur, you put those into the mix, and now you're up to 99.9% or 5%, right? So 4 elements make up the bulk of the chemistry that we talk about in biology, and another 4 round out the list pretty thoroughly, and then you get to some relatively smaller flavors, relatively smaller players, things like sodium and chloride. And I had that Freudian slip of flavor. The salt gives food some flavors, right? But those elements on that list, boy, there's not much point in studying and learning about the chemistry beyond that list if you want to talk about biological systems. So, chemistry. Chemistry is, again, the study of matter, and ultimately, it's going to be the study of chemical reactions, how matter interacts with other bits of matter. I told you on Tuesday, when I was talking with you about what does it mean to be alive, that living and non-living things have essentially the same chemical reactions taking place within them. There's nothing special. We don't have any preferred or, past that lets us use some chemical reactions as opposed to others. The chemical reactions that take place in living things are the same kind of chemical reactions that take place in non-living things. The difference is living things tend to cause some reactions. They set up an environment where some reactions that they like happen more readily than reactions that they don't like. Right? But today, let's just talk about all reactions, and in another week or two, I'll talk with you about how we play this game of facilitating some reactions and discouraging others from taking place. But so let's get to talk about these chemical reactions and how these things come together. And to do that, I need to get as reductionist as you can possibly get, certainly in a biology class. I'm not even going to talk with you now about atoms. I got to take a step further down the scale and just talk with you briefly about subatomic particles. And there's, physicists imagine and have created and have characterized on the order of 2 or 3 dozen different subatomic particles. I got good news for you. For a biologist, you really only need to keep your eye on 3 of them. And I can tell you guys have already been exposed to these 3 and talked about them a fair bit in other classes, but for the sake of completeness, let's just do it right now. There are 3 important subatomic particles for biologists, right? There are protons, there are neutrons, and there are electrons. Neutrons have no charge, negative or positive, right? Hence the name neutron. They're neutral. And they're really small. 1.7 times 10 to the negative 24th gram is the weight of a single neutron. Now, it may seem to you guys that I've just spouted out some trivia that could come in handy for you in a Trivial Pursuit game someday. I don't think you have to worry about that bit of trivia for the exam. I happen to know that number in my head. The fact that I've got some neurons that I've committed to remembering that number, well, maybe that means you guys should pay a little more attention to it. I didn't look at my lecture notes to dredge that up. I didn't look at the screen to dredge that up. I happen to know neutrons, 1.7, 10 to the negative 24th gram. I don't think you guys have to know that specific number to do well in this class, but here's a good idea. Appreciate that's really small, right? So just maybe make a mental picture, and for your mental picture, a neutron, really tiny, right? Maybe this will help you. 10 to the negative 24th gram, right? A packet of sugar from a restaurant, like McDonald's, typically has 2 grams of sugar in it. Throw half of it away, we got a gram. 10 to the negative 24th is a millionth of a millionth of a millionth of a millionth of a gram, right? So it's not just a millionth of a gram. It's not just a millionth of a gram. It's a millionth of a millionth of a millionth of a millionth of a gram. So for your mental picture, a neutron is insanely, unimaginably tiny. Good? Right? So in the scheme of things, neutrons, really, really small. Protons, happily, there's so much about chemistry that seems to be set up to make life easy for a biologist, but protons happily have the same weight, the same mass as a neutron, 1.7 times 10 to the negative 24th gram. So protons and neutrons are both crazy small, but they differ from each other in that neutrons have no charge, protons have 1 positive charge associated with them. Okay? Protons and neutrons hang out together in atoms. They're found within the nucleus of an atom. Okay? The number of protons in an atom ultimately are going to determine what kind of atom we're talking about. And I'll get to that in another couple slides. So different atoms have different numbers of neutrons and different numbers of protons, but neutrons and protons, excuse me, are very small, and they hang out together in the nucleus. The third player, the electrons, are smaller still. Okay, this is as small as you can get in a biology class. An electron is 1/2000th the weight of a proton or a neutron. So if you thought the protons and neutrons were crazy, unimaginably small, you need to push your boundaries just a little bit further on the smallness scale, because electrons are smaller still, 1/2000th the weight of a proton or a neutron, really, really small. And electrons, no great surprise to any of you, I would expect, are negatively charged. Every electron brings with it one negative charge that perfectly offsets and balances the positive charge associated with a proton. Okay? And what ends up happening in nature? Nature doesn't like to have charges separated. Wherever you have a proton with its positive charge, you typically have very nearby, relatively speaking, an electron with its negative charge to balance those charges out. Okay? Funny thing about matter, funny thing about atomic structures at the subatomic level is atoms are surprisingly empty space. I mean, you think about this tabletop here, feels awfully solid to me. The reality is that at a subatomic level, the vast majority of that is empty space. 99.9% is actually empty space, because the distance between where the nucleus is, the protons and the neutrons, and the electrons is really big. So let me give you a visual example here. I happen to have an actual silver dollar in my pocket, real silver dollar in my pocket. I keep it as a good luck charm, right? So I got a silver dollar in my pocket, and if you were to imagine that this is an atomic nucleus, it's a ridiculously large atomic nucleus, right? But an electron that might be associated with this atomic nucleus could be like Gavin, way back there in the back. Gavin, would you raise your hand for me? All right? That's where electrons associated with this atomic nucleus would be hanging out, right? And all that space between the nucleus and the electron, it's empty. Nothing's going on. All right? And so when I tell you atoms are largely empty space, that's what I'm trying to strike home, is there's a lot of space between where the neutrons and the protons are and the electrons are. All right? There you go. That's subatomic structure for you. Gives you a mental picture, I hope, of atoms. And when you put all this stuff together, I said a few minutes ago that if you have a different number of protons, we start now talking about different atoms, and in turn about different elements. I've said a couple times now there are 92 different naturally occurring elements. That means there are 92 different numbers of protons within atomic nuclei in nature. You can make more in the lab, not you and me, but physicists can. But there are 92 that occur in nature, and each of them has a different number of protons. Let's start with the simplest. The simplest atom is simply hydrogen with one proton in its nucleus, and then therefore one electron balancing off the positive charge of that proton. Okay? That's an atom. A proton hanging out by itself, doing nobody any harm. One proton, that's a hydrogen. That's a hydrogen nucleus. And if you put an electron with it, we got a nice, happy, stable system there. Negative charge balanced by the positive charge. Life is good. We call that arrangement hydrogen. Period. That's what hydrogen is. But if instead of hydrogen, we start talking about an atomic nucleus that's a little bit fancier, right? We could talk about something that has two protons in the nucleus. And two protons in the nucleus means we're talking about a different atom, different element, different set of chemical characteristics, 2 protons in the nucleus means we're talking about an element called helium. Okay? It happens that helium, in addition to 2 protons in the nucleus, typically also has 2 neutrons in the nucleus. And because there are 2 protons in the nucleus, there are also 2 electrons bopping around far away from the nucleus, but they're to help offset the positive charge of the protons. So, hydrogen, 1 proton, 1 electron, that's it. Helium, 2 protons, 2 neutrons, and 2 electrons. That's it. The number of protons is a big deal. Okay? Again, it determines which atom, what element we're talking about. It's such a big deal that it gets its own special name from chemists, and biologists glom off of it and use that same name. The number of protons in an atom's nucleus is called the atomic number. Okay? Each of the 92 elements has a different atomic number, meaning each of the 92 elements has a different number of protons in the nucleus. Hydrogen's atomic number is 1. Helium's atomic number is 2. Good? Carbon's atomic number is 6. See how they put that subscript 6 before the capital letter C, the symbol for carbon? The atomic number, if it's shown, is shown as a subscript that comes before the atomic symbol. Here, C for carbon. What can you guys tell me right off the bat here about how many protons carbon has? 6, because that's its atomic number. That's what that 6 means. Carbon's got different chemistry than nitrogen, which has an atomic number of 7. You know why? It's because carbon has 6 protons in its nucleus and nitrogen has 7. That makes all the difference. And it accounts for all the difference between the chemistry associated with carbon and the chemistry associated with nitrogen. Cool? So, I'm pointing at carbon here. All right? Carbon, most of the carbon that our bodies are made out of, the atomic nuclei, 99% of our carbon atoms, my carbon atoms, your carbon atoms, 99% of our carbon atoms are configured in this way. They have 6 protons in the nucleus and 6 neutrons in the nucleus and 6 electrons associated with them somewhere else. Okay? The atomic mass of carbon, how much a carbon atom weighs, is determined largely by just the number of protons and the number of neutrons. Because remember, electrons are chump change, 1/2000th the weight of the protons or the neutron. So if you want to talk about atomic mass, pretty much keep your eye on the big guys, the neutrons and the protons. Most of the carbon in our bodies has 6 protons and 6 neutrons. 6 plus 6, 12. That's, you've probably heard on TV shows, if not in other classes, that about carbon-12. That's what they're talking about when they're talking about carbon-12, because we have 6 protons and 6 neutrons in most of carbon's atomic nuclei. But there are other versions of carbon. They're called isotopes. Okay? An isotope has the same number of protons, but can have a different number of neutrons. So most of our carbon is carbon-12, 6 protons, 6 neutrons. About 1% of the carbon in our bodies is carbon-13. What do you suppose is going on there? 6 protons and 7 neutrons. A fairly stable relationship, or a fairly stable, configuration. But I say fairly because it's not as stable, it is not as permanent as 6 protons and 6 neutrons. Carbon-13, sometimes those atoms fall apart. A proton or a neutron, it's not stable. At the atomic nucleus level, a neutron can fly out, right, get lost, and you can go from carbon-13 to something else because you'll have lost some protons or neutrons. it's a radioactive isotope. Those particles, when they fly out of the nucleus, leave with lots of energy, and hence we call them radioactive. And in shorthand, you could call carbon-13 a radioisotope. It's a radioactive isotope of carbon. And in nature, we also find a third kind of carbon atom, carbon-14, where there are 6 protons and 8 neutrons. That's even more unstable of an arrangement and even more radioactive. There's not as much carbon-14 in the world as there is carbon-13 or carbon-12. But radioisotopes turn out to be really handy tools for biologists and molecular biologists to play with, because chemically, there's no difference between the way that any of those isotopes of carbon behave. They all act like carbon. And so what you could do is you could make glucose, which is a compound made out of carbon atoms, oxygen atoms, and hydrogen atoms. You can make in a laboratory glucose that has, instead of carbon-12, carbon-14, and then feed that to something. Let's make it a rat as opposed to you or I, but feed that carbon-14 glucose to something, and then look to see where in their body the radioactivity goes as that carbon-14 radioactively decays. We can use those radioisotopes then as a tracer to let us see how glucose gets moved through the body, how it gets metabolized, how long does it take for it to get released as carbon dioxide, and things such as that. So radioisotopes can really be very useful, very helpful tools. Ultimately, they're useful because carbon-12, carbon-13, and carbon-14, while they may have different numbers of neutrons, all have the same number of protons in their atomic nuclei, and therefore all behave the same at a chemical level. Okay? So, carbon-14, 6 protons, 8 neutrons. What about the chemistry of something that has 7 protons and 7 neutrons? Same total number, the atomic mass is 14, just like carbon-14, but you know what? I slipped something in on you there maybe. I said 7 protons, all right? That's not carbon anymore. Something with 7 protons in the atomic nucleus, we call it something completely different. That's nitrogen. So it's the number of protons that determines the atom, not the number of neutrons. It's the number of protons, and if you start changing the number of protons at the atomic nucleus level, we're not talking about the same elements anymore. And again, they act differently, and in the next 15 minutes, I think you guys are going to have a really deep understanding as to why they act differently. Let's check it out, right? Each of these different elements that I'm sure you've heard of before, hydrogen has a different atomic number. Hydrogen's got 1 proton, helium 2, lithium 3, beryllium 4, boron 5. Who cares about beryllium and boron, right? Not one of the 25 that are essential for life, certainly not in the top 4. The ones you guys are really going to want to focus on, hydrogen, carbon, nitrogen, and oxygen. Each with a different atomic number. Here 1, here 6, 7, and 8. Okay? So, look what I have done to you in the span of, 15 minutes. We've talked about what atoms are. I've talked with you about what isotopes are. Let me spend a few minutes now talking with you about some of the energetic considerations as they pertain to atoms and atomic nuclei. And I'll start off with something pretty simple. You know, this is almost just a vocabulary thing to get past here, but I'm going to occasionally be talking with you about kinetic energy as opposed to potential energy. Kinetic energy is the energy of motion. Okay, it's momentum. It's how fast and how much mass is getting moved. So kinetic energy is the energy of motion. Potential energy, you can dress it up and, use a lot of fancy words, but at the end of the day, potential energy is the potential to have kinetic energy. Okay, so it's not moving right now, but it's set up in a place that would allow it to move real fast or real hard because of where it happens to be. You know, I give you an example in the lecture notes about a rock in the Empire State Building, right? The higher the floor, the more potential energy that rock will have. Say you're on the 20th floor and you drop the rock out the window, it's going to convert that potential energy to kinetic energy pretty fast, and it'll deliver that kinetic energy to whatever it hits when it gets to the ground floor. Okay? If you took that rock to the 21st floor as opposed to the 20th floor, it's going to have more potential energy, and when it hits the ground, it will have had accumulated more kinetic energy. So kinetic energy is the energy of motion. Potential energy is essentially the potential to have kinetic energy. And how does that matter at all from a chemistry, or better, a subatomic particle kind of perspective? It's all about the electrons, okay? The energy that we'll be talking about in this class, ultimately in this class, the next class it will be a little bit different, but in this class, we're talking about the energy that electrons have. And electrons, the further out they are from a nucleus, the more energy they have. Plain and simple. Right? I'm inclined to want to go on and tell you other things about that, but that's the whole point. The further an electron is from an atomic nucleus, the more energy it has, the more potential energy it has. Electrons that are far out have a lot of potential energy. Electrons that are close in have less potential energy. Okay? Some electrons can be really far out. All electrons are pretty far out, like Gavin back there, right? But some of them can be further out still. To move an electron from a low energy state, from a low potential energy to a higher potential energy, you know what you got to do? It's not really complicated, not tricky. You got to give it more energy. You got to juice it up. You got to jack up its energy to push it out further from the atomic nucleus. You need to deliver to that electron a packet of energy. And those packets of energy are almost always photons, light, right? Photons are little bundles of subatomic energy that can be delivered to things like electrons to juice them up, to crank them up to a higher level of potential energy, to bring them further away from an atomic nucleus. And when an electron with a lot of energy falls from a far out position to something closer to the atomic nucleus, guess what? It has to release a packet of energy, like a photon. And packets of energy usually have fairly discrete amounts of energy associated with them. To get you from one orbital to another orbital requires a pretty specific amount of energy. That specific amount is often referred to as a quantum, a quantity of energy, and hence there's the old TV show Quantum Leap. That's where it gets its name from. You're leaping from one electron orbital, from one layer that's close to the atomic nucleus to one further out. You do that by absorbing a photon, a quantum of energy, and to fall back, you have to release that photon, that same quantum of energy. Okay? So, long story short, the closer an electron is to an atomic nucleus, the less energy it has. The further out, the more energy it has. Good enough? Now, I've mentioned the word orbital a couple of times. And the next couple slides are going to show you some pictures of orbitals. Let me just move to that. But as I'm doing that, let me tell you, orbitals for subatomic particles, orbitals for electrons, are different than the orbits for a planet, right? An orbital for an electron tells us, it's a prediction about where a given electron will be 90% of the time, right? So it's like a volume of space centered on an atomic nucleus. 90% of the time, an electron will be within that sphere or that space that we've called the orbital. Okay? And different atoms typically have different numbers of electrons. Hydrogen typically has, it always has one proton, and it typically has one electron to balance off the charge. So hydrogen has one electron, and look what they've done in this periodic table for you here. They show you an atomic nucleus here, and then they show you a circle that's supposed to conjure up the image of an orbital, and on that orbital, they put one dot. That's supposed to make you think of one electron in that orbital. Okay. Helium, with its 2 protons, typically has 2 electrons, and look at that, the orbital here has 2 dots. To help you remember, oh yeah, 2 protons probably means there's going to be 2 electrons to balance out the charge. Funny thing about electrons is they're negatively charged. I don't think that's so funny in and of itself, but they don't like each other. And it's because they can't handle each other's negativity. Okay? Think of it in those terms if you like. But those opposites attract. The protons and the electrons come together, but the like-charged electrons just can't handle being in the same space that much. No electron orbital can accommodate more than 2 electrons at any point in time. They just can't get along well enough. And so once you've gotten 2 electrons associated with an atomic nucleus, if you want to add 4 more, there's no room at that lowest level of energy anymore, that orbital that's closest to the atomic nucleus. You got to look further out, and you start to fill up electron orbitals where the electrons have to have more energy associated with them, a little further out. So I'm pointing again at carbon. All right? You remember, I hope, that carbon has 6 protons, either 6, 7, or 8 neutrons. Doesn't matter. It's going to have the same number of protons, therefore the same chemistry. 2 of those electrons, there's 6, right? 2 of those electrons are hanging out in the lowest energy orbital that they can find. Just like people, electrons like to be in the lowest energy state they can be. Okay? Nobody in this room, one person's stair climbing, nobody in the room is doing jumping jacks. All right? Why? Well, we're lazy. Believe me, if I thought I could pull it off, I'd be sitting down. I'd get a couch in here, and I'd be lecturing from the couch. Right? We're all lazy. That's just the way we are. Electrons want to be in the lowest energy state as well. So the first thing that happens with electrons is you fill up the lowest energy state available. Think of it, right? If we had 2 lazy boy chairs down here, there'd be people sitting in them. If they could get to them before I did, somebody would be sitting in them. Once those get filled up, people are going to use the less comfortable chairs a little further out. So the electrons, you fill up the lowest energy orbital, but then you still got 4 more electrons to go. Where are you going to put them? Well, there's another level of orbitals, the level 2 orbitals, and you can put electrons into there. And so for carbon, what we've got is 2 electrons at this level of energy, and then we spread 4 more out at the next level of energy. And I'm going to show you in a moment a picture of where those electrons look like, the actual picture of these different orbitals, but that's what's going on with the orbitals. I'm going to tell you something now. I don't know if this is the best time for me to tell it to you, but I want to tell it to you 3 or 4 times. And so this is my first time to tell you, because this is really important. Okay? What determines the chemical activity of an atom is what's going on in the outermost shell of the electron orbitals. It's the electrons that are far away from the atomic nucleus that govern, that determine, that dictate how that atom is going to behave chemically. That is determined by the number of protons in the nucleus, so you could say that's where all the action is, but where the rubber, and this is it's actually a literal analogy, but where the rubber is hitting the road isn't what's going on at the atomic nucleus. Remember, atoms are mostly empty space. When one atom bumps up against another atom, it's not nucleus bumping into nucleus, it's the outermost shell of electrons bumping into the outermost shell of electrons. Right? What determines the chemical activity of any element is what's going on, what kind of electrons, how many electrons are there, and how happy are they at the outermost reaches of that atom's electron orbitals. So, let's take a look at these. Here's a very simple but a zoomed-in version of the same sort of circles that you saw on the previous slide. Right, you got a big thing in the middle there, that circle, the gray circle is an atomic nucleus. Next out from the atomic nucleus is an orbital called the level 1 orbital. Okay, very cleverly named. You got to hand it to those chemists for their imagination with the names for that one, right? The closest orbital to the atomic nucleus we call level 1. And that orbital is spherical in shape. So you could call it a level 1s orbital, S for sphere. And that one orbital can handle, it can make room, it can accommodate up to 2 electrons. But once you've got that orbital full up of electrons, if you have more electrons to carry around with you as an atom, you got to push them out further from that lowest level. The next level up, again, what do you think? If you guys met many chemists, do you think they're wild and crazy and come up with imaginative names? They don't. I have lots of personal experience. The next level up is not very imaginatively named, the level 2 orbitals. You know, something like Fred or George would have been fun, but no, they went from 1 straight up to 2. Okay, so the next level out is 2, and unlike the level 1, all atomic nuclei have just one level 1 orbital. There are actually 4 different level 2 orbitals, where the electrons within these different orbitals all have about the same amount of energy associated with them. And each of those 4 level 2 orbitals can handle up to 2 electrons. So, you got a first shell, the level 1 orbital. This is 1s, and you got a second shell with the level 2 orbitals, 4 different level 2 orbitals. Look at them, 1, 2, 3, and 4. When you're talking about an atomic number of 10, like neon, what you got is 10 protons here in the nucleus and 10 electrons around it. 2 of those electrons will be at level 1, and the other 8 will be 2 each to the 4 level 2 orbitals. It's a full house. Nice, complete outer shell for neon with its 10 electrons. 2 at level 1, 8 of them at level 2. That's all you need. Let's look even a little more closely at what these shapes are. Here are level 1, 2, and both kinds of 2 in all their glory. Once again, I got good news for you. As a chemistry major, at some point, you got to get up to level 3 and level 4 and even level 5 talking about electron orbitals. Biologists, we got it made. We never worry about anything beyond level 2. Don't get worried about it, certainly not for this class. You never have to worry about anything beyond level 2. It's all about what's going on at level 1 and level 2. Level 1, there's one orbital, it's spherical, 1s, it can hold 2 electrons. Level 2, there are actually 2 different kinds of level 2 orbitals. There's a spherical one, 2s, and then there are 3 of them. And I've never understood this. The chemists, maybe I'm getting a bit of insight. The chemists think that this blue line here, that shape, get this, they think that's dumbbell shaped. All right? I've been to gyms. I use dumbbells. That doesn't look like any dumbbell I've ever seen. But they'll tell you that the 2 p orbitals, and who knows where p came from, but the 2 p orbitals are dumbbell shaped, and there are 3 of them pointing out in different directions. Okay? One level, 1 orbital, 1s, holds 2 electrons. 4 level 2 orbitals. One of them is called 1s, it's spherical, and the other 3 are 2p orbitals. They are dumbbell shaped. All right? Big deal here is each of these orbitals can handle up to 2 electrons. 3, bad, not going to happen. 1, yeah, that's okay. 0, not too big of a problem. 2, cool, right? So each of these orbitals can handle up to 2 electrons. And when you look at them all taken together, that's sort of how the atom is hanging out. And let me say it another time. What determines the chemical activity of an atom is not what's necessarily going on at the nucleus, right there, but rather what's bumping up against other fringes, the orbitals at the fringes of other atoms. Okay, so it's stuff happening far, far away from the nucleus that's going to determine the chemical reactivity of each of these atoms. So that's all 3 of those things taken together. Now, this isn't really biology, right? This is chemistry, unapologetically chemistry. But it's important to biology because what's going on at those outermost shells of the atoms determines the chemical reactions, and the chemical reactions, much as we may resist it, an awful lot, if not all, that makes us what we are is a bunch of chemical reactions. So let's make sure everybody's cool with how those chemical reactions take place. And what I'm going to tell you in the span of the next, hopefully, 5 or 10 minutes, to me, and I'm a strange guy, I'll grant you that, but to me it was a revelation. There's just like, oh, I get it. I understand how all of this stuff plays out. It took something like 4 years of taking chemistry classes before I really understood this, and I hope in 5 or 10 minutes I can get you guys to just have the answer key effectively to all of chemistry. What I want to talk with you about right now is something called valences. There's this guy, dead now. Well, let me start this way. Think for a moment. I'll give you like 5 seconds. Think, who's the person you're most proud or pleased or excited that you had the chance to actually meet? Any of you actually shake hands with or meet a president? A lot of people, that's pretty high. Anybody meet or shake hands with Oprah Winfrey, right? Yeah. Who? Some rock star, right? Who? I'll tell you who it is I'm most excited that I've had a chance to meet, and I bet none of you have met this person, and none of you can because he's dead, right? If you haven't by now, you missed your chance. Linus Pauling, all right? That's the guy I'm most excited that I had a chance to meet. Most of you don't even know who Linus Pauling is, and I'm still cool with that, but I know who Linus Pauling is, and I'm excited that I had a chance to meet him. Linus Pauling is the only person to have ever won 2 Nobel Prizes in different disciplines. He got a Nobel Prize for chemistry and a Nobel Prize for peace. Pretty cool. I not just met Linus Pauling, I sat next to him at a meal. I had him put like a mountain of vitamin C on a salad that I was eating. Good stories, right? Come down and chat with me sometime. I'll tell you all sorts of cool Linus Pauling stories. But he got 2 Nobel Prizes, first for chemistry. Guess what his chemistry Nobel Prize was for? It's for a book that he wrote, a treatise that he wrote, called The Nature of Chemical Bonds. And you know what it's all about? It's all about valences. So he gets a Nobel Prize for figuring this out. And again, to me, it's like the answer key to pretty much all of chemistry. It's like, oh, okay, so that's what's going on. I've made a big deal about them, these valences. What are they? Let me tell you what valences are. Valences ultimately, valence, the word means, we're talking about the electrons in the outermost shell of an atom, right? But the key here, it's the number of unpaired electrons in the outermost shell. That's what's really going to be important. That's what drives the chemistry of all the different elements that occur naturally and unnaturally, for that matter. It's the number of unpaired electrons in that outermost shell. Check this out. What's the valence of hydrogen? It's got 1 electron by definition, it's unpaired. It's by itself. There's no pair, right? There's one, not two, one, right? There's one electron in its outermost shell. Hydrogen has a valence of 1, right? And it has one unpaired electron in that outermost shell. What are the other three elements that we worry about in biology? Carbon, nitrogen, and oxygen. Forget about all the rest, at least for now. What's the valence of carbon? Better, what's the number of unpaired electrons for carbon? Check carbon out. It's got 2 in the level 1s, 6 protons, meaning 6 neutrons, meaning, well, 6 protons, certainly meaning 6 electrons. 2 of those electrons are hanging out in 1s as a pair. I don't care. That's not the outermost level anyway. 4 of them are hanging out at level 2. There are 4 level 2. 1 of them will be in each because they don't want to be next to each other if they can help it. Equivalent energy, outermost shell. Carbon has a valence of 4. Carbon has 4 unpaired electrons in its outermost shell. All right? So hydrogen and carbon are different. You know what? Hydrogen has different chemical properties than carbon. You know why? It's because carbon has 4 unpaired electrons in its outermost shell, and hydrogen has 1. It gets better. There's still 2 to go, right? Nitrogen, check it out. It's got an atomic number of 7 protons, 7 electrons. 2 of those electrons are hanging out in the level 1. Let's not worry about them. 5 of them are hanging out at level 2. There are only 4 level 2 orbitals, so I can take 4 of the 5 away, but I still have 1 left that I got to plug in with another electron to pair up with another electron, but I still have 3 unpaired electrons. Hydrogen has 1 unpaired electron. Carbon has 4 unpaired electrons in its outermost shell. Nitrogen has 3. Is there something missing? I've only talked about things that have 1, 4, and 3. Oh, thank goodness there's oxygen. Check that out. Atomic number of 8, sorry. 8 protons, 8 electrons and neutrons. 2 of them are at level 1. Forget about them. 6 of them are at level 2. 2 of them are going to be paired. There are going to be 2 pairs of 2 and 2 unpaired ones left behind. Do you see what happened here? Nobody here is nearly as excited as I am about this. Not one of you. And I understand. That just means that I'm getting ahead of myself. I'm seeing the bigger picture before I share it with you. Check it out. I got one of my elements. One of my atoms has 1 unpaired electron. Another has 2 unpaired electrons. Another has 3 unpaired electrons. And the last has 4 unpaired electrons. Each of them is going to have a different chemical activity because of the difference in the number of unpaired electrons. And I got the whole palette there. I got a little bit of everything. If I need something that acts the way things act when they have only 1 paired electron, I got something for that. I use hydrogen when I want to make a chemical compound with a certain chemical characteristic. When I want to have something that acts the way things act when they have 2 unpaired electrons, I'm cool, I'm good. I go to the bucket that has my oxygen in it. When I want something that acts like it's got 3 unpaired electrons, no problem. I'm all over that. My bucket of nitrogen's right over there. I want 4 unpaired electrons, there's carbon. I want 5 unpaired electrons, I can't do that. There's nothing that has 5 unpaired electrons, at least not within the naturally occurring elements that get used by our bodies. I'm trying to conjure up in your minds here the idea of a painter's palette, right? You know, we got 4 primary colors. I think I'm a scientist. I don't know about these things. So you got these primary colors you work with, and you mix them up in different combinations to get all the hues of the rainbow, right? I got the 4 primary kinds of chemicals to work with here in their chemical activities, and I can mix them up in different ratios and different combinations, making compounds that have different chemical characteristics that ultimately are a combination and derived from what I'm getting from those 4 elements. That's why we only use 4 for 96% of the mass of our bodies. We got it all right there. It gets the job done. And how many of you are fans of Star Trek, the original series? At least a couple. I cannot have just one or two Trekkies out here. When I was a kid, Star Trek, the original series, was in first reruns. I'm an old guy, but I got to see them when they were still really fresh. If you haven't seen the original Star Trek series, this is going to go right over your head. But let me tell you a story, because at one point in the original Star Trek series, the writers were taking to heart some pretty valid criticisms. People were saying, how could it be that all the aliens just look like people that have pointy ears? Right? Oh, what's up with that? Shouldn't there be some stranger looking aliens than that? And the writers said, oh, yeah, that's a good point. What's the wildest thing that you could come up with that's, could be plausibly alive, but isn't obviously a human wearing pointy ears, right? And guess what they did? To their credit, they went and they talked to some biologists, and they asked, so, what would be wildly different, right? Plausible, yet wildly different. And the biologists came up with something kind of clever. They said, well, here's this. All life that we know on Earth is carbon-based, right? Why don't you do something that's different than carbon-based? What's a suitable alternative to carbon? And I can ask you guys that. What's a suitable alternative to carbon? Carbon, what makes carbon important is it's got 4 unpaired electrons. What else up here has 4 unpaired electrons? There's only one thing. It's silicon. Silicon has its level 2 filled out, but it's got 4 unpaired electrons at level 3. It's got 4 unpaired electrons, and hence the Star Trek creature called the Horta. It's a rock living thing on some planet, and I may even have a slide of it for you at some point. I talked about the Horta last fall to this class, and I got to tell you, I get a lot of interesting questions from students. Right after class, a student comes to me and he says to me, so how much do I need to know about the Horta? Do I need to, I hadn't heard about these silica-based life forms before, who discovered them, where are they from? I was like, oh my gosh, okay, Star Trek is fiction, right? It's not real. But if you wanted to think of some alternative to carbon, something that would make sense would be to go to silicon. If you wanted something as an alternative to hydrogen, what do you need? You need something with 1 unpaired electron. You got a couple choices. You could go for lithium or you could go for sodium. They each have 1 unpaired electron. What did we choose? We chose hydrogen. We're based on hydrogen, carbon, nitrogen, and oxygen. You could have been lithium, silicon, phosphorus, and sulfur. We're not. We're these 4, right? And we're those 4 because they give us the complete palette. Let me show you now how these palettes come into play. So we've talked a little bit about valences. Let me tell you now about chemical bonds. There are 2 rules that drive chemistry at an atomic level. One of them is that nature absolutely abhors a separation of charge. Nature does not like it. When you got a lot of negative charge over there and a lot of positive charge over there, you need to have them kind of close together, right, to offset each other, to balance each other out. Nature can't stand a separation of charge. And that includes the idea you can't fit 2 electrons too close to each other either, because the charges are not separate. You have 2 similar charges there. You need to have opposite charges to balance each other. So nature doesn't like it when you've separated charges. And rule number 2, imposed on us by nature for all chemistry, living and non-living, is nature really seems to be hung up on the idea of wanting the outermost shell of electrons for any atom to either be completely full or completely empty. It's a hang-up nature has, okay? But that's the rule. And it's an important rule. It's not as important as the first rule, but there's the rule number 3 is so distant that nobody can agree what rule number 3 is. Chemists, physicists, biologists, we all agree. Rule number 1, no separation of charge. Rule number 2, completely full or completely empty outermost shell. Carbon, well, let's start simple. Hydrogen has a problem. It satisfies rule number 1. There's 1 electron for the 1 proton. That's cool. Nature's happy about that. But rule number 2 is an issue for hydrogen. Because remember, rule number 2 is you want that outermost shell for hydrogen. It's 1s, level 1s orbital. For hydrogen, you got a problem. You got 1 electron there. That 1s orbital is, depending on how you look at it, it's either half full or half empty, but it sure ain't, excuse the language, it sure ain't full or empty, right? Because there's an electron there. There's not 2 electrons there. There's not 0 electrons there. There's 1. So how do we make nature happy? Nature doesn't like that. We should try to make nature happy, right? How do you make nature happy in a circumstance like that? The way you make nature happy in a circumstance like that is you get something like 2 hydrogens, each with the same problem, each with an electron orbital that is half empty, and you bring them together. And you let their outermost shell of electrons not just rub up against each other, but overlap each other. All right? So here we got these 2 hydrogen atoms, each with 1 electron in its outermost shell. And if you bring them together, look how the orbitals are, ooh, you look friendly, let's hang out together. And you get to a point where that 1s orbital for the 1 hydrogen atom physically overlaps with the 1s orbital for the other hydrogen atom. And each of their electrons gets shared between those 1s orbitals. At any given point in time, nature's, oh, what are you doing? Hydrogen atom number 1, what are you up to there? Oh, I'm cool. I got no electrons in my outermost shell. My electron went over there. He's hanging out with the other hydrogen. Oh, okay. That's cool. Hydrogen atom number 2, what you doing? You okay? What's happening over here? I'm cool. I got 2 electrons, right? I got that guy's electron. I got my own electron. My outermost shell is full. Between the 2 of them, they can make nature happy by sharing that electron. The electron spends some time over on hydrogen number 2, sometime on hydrogen number 1, but at any given point in time, there's a pretty good chance that one of them will have an empty level 1s, and the other will have a full level 1s. That sharing of an electron between those 2 atomic nuclei gets a fancy name. That's called a chemical bond. When you share electrons between atoms, you've made a chemical bond. And check this out. The number of chemical bonds that an atom can make is determined by the number of unpaired electrons in its outermost shell. Hydrogen has 1. You can never make a valid chemical structure involving hydrogens that have more than 1 hydrogen bond. Or, I'm sorry, more than 1 covalent bond, more than 1 chemical bond. I'm using other words here. I'll get to what these all mean in a minute. But hydrogen makes 1 bond, 1 chemical bond, because it has 1 unpaired electron. Oxygen can make 2 chemical bonds because it has 2 unpaired electrons. Nitrogen can make 3. Oxygen can make 4. How about that? We got the whole palette again. You need something with 1 bond, I can help you there. I reach into my hydrogen bucket. You want 4? No problem. I got carbon for that. So, sharing of electrons between atoms is actually a very stable relationship. It satisfies this very important rule from nature's perspective in terms of either completely emptying or completely filling the outermost layer of electrons for an atom. And we can diagram, we can show those bonds in a couple of different equivalent ways. here in the electron distribution diagram. Do you recognize what's happening here? It's that nucleus, now with the letter H in it. There's the circle before they had the electron up here. Now look at that. They've very cleverly put it over here. And look at this. This one, instead of having its electron up here, it's down there. Notice how they're overlapping. That's what I've been talking about. This is a pretty good graphical representation of electron sharing between two atoms. That's a bond. And I'll tell you what, it's not just a bond. It's not just a chemical bond. It's what we call a covalent bond. Co, because they're together. Valent, short for valence. The valences are overlapping. Okay? But there are other ways you could depict this. You could use the fancy Lewis dot in structural formula. Look at that. They're showing you there are two electrons. Here there's just a line that shows you a sharing of the electrons. And you could even do a space-filling model. These are all equivalent. What your textbook uses and what most of the world uses to show a covalent chemical bond is simply a line connecting those two atomic symbols. That is a formula that gives you the structure and the composition of a compound that you know of as hydrogen gas. Okay? Hydrogen gas is a simple one. You can take it up a notch. And how many bonds can oxygen form? I've said this a couple times. It can form two covalent bonds, okay, two chemical bonds. Let's use the fancy word covalent. It can make two covalent bonds. Here's how the picture looks. Look, the level 1s is hanging out here still. Those two electrons are right up there. But the level 2, you can have two of the two p orbitals overlap with each other. It looks like this. Simply put, you can draw that with paper and pencil pretty easily. O for oxygen, two lines because there are two covalent bonds, and then another O. You can dress these things up in different ways. This is a perfectly happy, stable situation, right? We have oxygen who's crying out, please, what can I do to get just two more electrons, because nature doesn't like that I've got two unpaired electrons. And you got hydrogen saying, you know, I can go either way. I can give you an electron, I can take an electron, one or the other. Either of those will make nature happy. So you can hook up an oxygen with two different hydrogens and make this funky thing called H2O, water. That's the chemical structure of water. It's got two covalent bonds. And did you notice? It's going to make nature happy, and it makes nature happy because the outermost shell of all of those atoms is either completely full or completely empty, and it's all driven by the valence. It's all driven ultimately by the number of protons in the nucleus. That explains the whole shebang. There's one neat little subtle thing I'm going to toss out at you in a minute, but before I do, let me just, for the sake of completeness, show you carbon. Carbon's got 4 unpaired electrons. It can make 4 covalent bonds. Here's a gas called methane, methane, where you've got carbon making 4 covalent bonds with hydrogen. Each hydrogen makes 1. Carbon's got 4. Very happy. Outermost shell of carbon is full. Outermost shell of hydrogen is either full or empty, depending on how you're looking at it. Everything's cool. Here are all of them together. All right, I said there was one last subtle thing. And here it is. These three, let's do this. These three, okay, hydrogen gas, oxygen gas, and methane gas are different than this one. There are 3 things that make the first 3 things I pointed to have something in common that's different from the third thing. Here's what it is. The first 3 that I've talked about here, notice they're gases. All right? Hydrogen gas, oxygen's a gas, methane's a gas. Right? I think that's common knowledge. You don't need a biology professor to tell you that. They're gases. What that means is that they're pretty inert. They don't need to, they don't care to interact with other things very much. Right? They're kind of aloof. You know, Hydrogen gas really doesn't need anything from anyone. Nature is quite happy with it exactly the way it is. The outermost shell is either completely empty or completely full, depending on how you look at it. That's it. Don't need to say anything else, don't need to do anything else. The same is true for oxygen. Its outermost shell is completely full, right? Doesn't need anything. Methane gas, it doesn't need anything from any other compound. Water is different, and it's not a gas. It can be a gas, but it's at room temperature, not a gas. And the whole lecture on Thursday is going to be about on Tuesday of next week is going to be about the chemistry associated with water. But water differs from the rest because it does kind of need something from something else. Now let me show you what the problem with water is. Think about the oxygen. Let's start by talking about the needs of the oxygen. The oxygen has 6 electrons in its outermost shell. Okay? What's oxygen got to do to make nature happy? It either needs to bring in 2 electrons to round out to 8, or it needs to dish off 6 electrons to go to 0. I don't think it's hard to wrap your head around the idea that taking on 2 is a whole lot easier than dishing off 6, right? For a number of reasons. There's more work involved is one of them, but another is that if you dish off 6, you got this +6 charge associated with the atomic nucleus. That can't be good, and that's a -2 charge by bringing on 2 more electrons. That's probably not that good either, but -2 compared to +6, oh, I'll go with the -2, right, in terms of trying to make nature happy. The point is this. Oxygen has an affinity for electrons because by pulling electrons toward it, it's the easiest route that it has for satisfying that rule of nature, to either have a completely full or a completely empty outermost shell. Taking on electrons is easier for oxygen to do than giving them up. Think about hydrogen. Hydrogen is half full, it's half empty. It could go either way. You want my electron? Here you go. I got no problem with that. I'm happy that now I have none. You don't want an electron? I'm cool with that. Give me your electron. Now I got 2. I'm full. Everything's cool. When oxygen and hydrogen interact with each other to make a covalent bond, you know what ends up happening? Is hydrogen's electron actually spends more time near the oxygen than it does near the hydrogen. And that causes there to be a separation of charge. A little bit of a separation of charge. There's a whiff of negativity near the oxygen and whiffs of positivity near the hydrogen. Those are not just covalent bonds, those are polar covalent bonds because the electron spends more time on one end than they do on the other. And it ends up looking something like this. This little squiggle here is the lowercase Greek letter delta. It's used to denote partial. And the negative there means partial negative charge. There's a little bit of negative charge on the oxygen and a little bit of positive charge on the 2 hydrogens. And so unlike gases that have no separation of charge at all because of the equal sharing of the electrons between the atoms involved, water with its polar covalent bonds has some separation of charge, and that in turn sets up the potential for water molecules to interact pretty well with other molecules and do things like this. Here ammonia has a little bit of a negative charge. Here water has that hydrogen with a little bit of positive charge. If you rub this up against this, you make nature happy. You don't share the electrons. It's not a covalent bond. Instead, we call that a hydrogen bond because hydrogen is often involved with those bonds. All right, you guys have been patient with me. Let's call it a day. On Tuesday of next week, we're going to focus our attention on water and talk more about what makes it tick. Have a good weekend.